Welcome once again to our discussion on pool data, right? Yesterday we are talking about combining cross-sectional data with time series one, and we said that when we combine randomly collected independent cross-sections collected from a given population over a period of time, then we said that that is basically a pool data. Pooling cross-section with time series, that is called pool data when the cross sections are independent. So, we are discussing combining cross section with time series data. So, yesterday we talked about pool data and we said that this is basically combining independent cross section. So, here when we combine the cross section, we say that independent cross sections combined with time series data. Right. So, for example, we can say that let us say this is in first year we have collected data from these 4 forms. Okay. Let us say this is year 2000. Then in 2001 we are again collecting data from another 4 forms from the same industry, let us say E, F, G, H. So, another cross section in 2001, then I, J, K, L. In 2002, M, N, O, P. 2003. Now, if you look at these cross sections are actually independent because there is no commonality among these among the elements of these cross sections. In year 2000 it is ABCD form, in 2001 it is EFGH, in 2002 it is IJKL, and in 2003 it is MNOP. So, that means we have collected samples from different forms. We have collected some information from different forms at different point of time. Okay. Now, today we are going to discuss about another type of specific pool data wherein we are collecting information from the same individual, and if that is the case, we say that that is called panel data. So, in panel data what we are doing? It is A, B, C, D in 2000. Then in 2001 also it is A, B, C, D. Then in 2002 also it is A, B, C, D, and it is A, B, C, D in 2003. This is called panel data. So, that means here the cross sections are actually not independent because I am collecting data from the same individuals or same country or same states or same firms over a period of 4 years. So, here cross sections are not independent. Sections are related related. Data collected from same cross-sectional units same cross-sectional units over a period of time. Okay. All right. Now, what is the need of this type of panel data? What is the need of panel data? Yesterday, while talking about pool data, we said that sometimes we work with combining cross-sectional data with time series and make it as a pool because of its what is the advantage we get in pool data? Instead of working on a single distribution for the dependent and independent variables, in pool data we get multiple distributions of dependent and independent variables. So, information content in pool data is much higher, okay, compared to the cross-sectional data, and that makes the estimates derived from a pool data much more efficient and reliable compared to the cross-sectional estimates. Today, we will try to understand another advantage of working with this specific panel data, specific pool data, that is called panel. So, you have to keep in mind that panel data is also a pool data. It is a specific kind of pooling. Instead of pooling independent cross section, in case of panel we are actually pooling same cross sections over a period of time. Sometimes this is also again a specific type of panel where the number of observations are same and it is the same individuals or forms. So, A, B, C, D, A, B, C, D, A, B, C, D and A, B, C, D. So, that is why when in each year you have same number of observation, this is called balanced panel. But there is no guarantee that in each year you would be able to observe same individual or same form, because collecting a panel data is not a very easy task. So, for example, in 2000 we have data from A, B, C, D. It may so happen that in 2001 actually this firm C exited from the market, or somehow the data for the C firm is not available, right? Okay. So, in 2001 it may so happen that we have data on A, B and D. Similarly, in 2002 it may so happen that this C firm came back once again. Additionally, we may have data on E firm as well, right? And in 2003 we may not get again data on B and C, rather we may have E and F. This may also happen. So, that means in this type of pooling at least some individuals or some entities are common and there is some new element added in that distribution, in that cross-sectional units, right. So, what will happen in that case when number of observations are not same? This is called unbalanced panel. So, number of observations are not same over a period of time. So, that means now we can understand the panel data. So, panel data is of two types. One is called balanced panel. So, this is called balanced and this is unbalanced. unbalanced panel. Two specific type of panel data we have. So, when we have unbalanced panel, there is a tendency, generally what we do, we remove the uncommon elements and try to make it a balanced panel. Don't try for that, because you have to keep in mind, in econometrics, one observation means one piece of information, and information is very valuable in econometric estimation. Higher is the better. Higher the information contained, better would be the value of those estimates. So, that is why no need of throwing out any piece of information, no need of unnecessarily making an unbalanced panel a balanced one. Okay. So, we have to take information as it is, and then we will work with either balanced panel or unbalanced panel depending on the situation, because we have econometric literature for both type of panels. No need of making the unbalanced a balanced one. That is what I wanted to say. Then what we will do, we will try to understand another important objectives of this pool data or panel data. So, let us take an example. Suppose we are interested in estimating the relationship between crime rate equals to, let us say, we have estimated a relationship between crime rate and unemployment rate. So, alpha plus beta 1, let us say this is unemployment rate. Okay. So, let us say we have data only on 1987. So, for one period, this is for this is for 1987. Okay. So, we have data on crime rate, we have data on unemployment rate, and this is only available city wise data. We have data on several cities about their unemployment rate and crime rate only for a specific year. And what we hypothesize, that unemployment rate and crime rate, they are negatively related, which is quite logical, because as unemployment rate increases, so what will happen is, they are positively correlated. Higher is the unemployment rate, higher would be the crime rate as well, because if people are not employed, then they will be involved in several criminal activities. That is what the literature says, and that is what is our assumption is. But when we estimate this type of equation using a single cross section, it may so happen that we may get this type of relationship. Crime rate equals to, let us say, 128.38 minus 4.16 unemployment. Okay, it may so happen. So, that means here we are getting a negative relationship between unemployment and the crime rate, and this may not be insignificant, this may be insignificant also. So, what is happening when we are working with a single cross section? First of all, the coefficient of unemployment, it is giving a wrong sign. It is not as we were expecting, because as unemployment increasing, crime rate is decreasing, which is difficult for us to believe. So, this is against the theory. And secondly, this coefficient is not significant also. Then the question is, why is it happening? Why is it happening? It is happening because in this simple relationship, crime rate and unemployment rate, this equation may suffer from several city specific city specific unobserved effect. Unobserved effect. Okay, this is a simple relationship. So you can include many variables, city specific variables which are observed. So you can make it as multiple linear regression model, like what is the distribution of education, average education in that city, what is the religion, what is the income status, so on and so forth. But there are certain city specific features which are not directly observable. Maybe the geographical location, maybe the history of that city. For example, if we collect crime rate across several Indian cities, then it may so happen, let us assume that Mumbai shows the highest crime rate. Okay, highest crime rate. Then you can include several variables like unemployment rate, religion, average education, average income, so on and so forth. But there are certain features of this Mumbai city which is unobservable. It may so happen that historically the nature of the city itself is such that there is high crime rate, which is difficult to explain. So in that case, what we can do, instead of running the regression only on a particular year 1987, we can add another specific year, let us say in 2002. So what we can do, we can add another year, let us say 1982, and make it a panel. Now, when I am adding one previous year observation on crime rate, unemployment rate, basically what I am trying to do by this, so with this we try to capture the history of the city as far as crime rate is concerned. Okay. So we have two periods data, 1982, 1987, and we have collected information from the same cities. So as a result of which, this will become a pool, a specific type of pool, which is panel data, and adding the previous year's information makes this data capturing the history of the cities, as far as this crime rate is concerned. So this is one way we can, this is another advantage of capturing, another advantage of panel data to capture history of the city, which is which are unobserved in terms of city specific information. Okay. Now what we will do, there is another way of looking at this. Hello. 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 Old days, you come tomorrow morning. Yeah, before 12 o'clock. Now, there is another way of looking at this model. Let us say that in this equation, we are modifying the equation as crime rate, or let us say the crime rate is denoted by now YIT equals to, yit equals to beta 0 plus delta 0 dt, okay, d, or let us say d 2t plus beta 1 xit plus ai plus uit, where d 2t equals to 1 if second period 0 otherwise. Okay. Now, what is the additional feature of this model? Here, look at this. I have included a factor called AI. And what is AI? This AI is called city specific unobserved effect which are fixed over a period of time. Okay. So, this AI call city specific unobserved effects which are fixed over a period of time. So, that is why AI is called individual specific time fixed effect. Individual specific time fixed effect. That means, while modeling crime rate and unemployment rate, we accommodate the fact that several cities, they have certain city specific features which are difficult to observe, but that does not change over a period of time. Okay. If that is the case, then this would be our modeling. So, look at this. Here we have included one year dummy D2T to represent the fact that at different point of time, distribution of this YIT and XIT, they are different. We also accommodate the fact that there are several cities, they have city specific unobserved effect. And that is captured by AI, right? That is captured by AI. So, this should be our modeling of a simple panel data, which is called fixed effect model. Why this is called fixed effect? Because we have included this is called a fixed effect model. Fixed effect model. What is fixed here? The city specific features are fixed over a period of time. That is why it is called fixed effect model, right? Now, the question is, can we apply OLS to estimate a fixed effect model? Can we apply OLS to estimate a fixed effect model? Now, to estimate a model using OLS, what is required? That so now we can modify this equation as YIT equals to beta 0 plus delta 0 d2t plus beta 1 xit plus, let us say, VIT, which is equals to AI plus UIT. So, VI is basically a composite error term consisting of the unobserved effect plus this idiosyncratic error. Okay, we have the idiosyncratic error UIT and AI. So both are actually unobserved. Both are unobserved. So AI is also like an error term. The only difference between AI and UIT, AI varies across individuals, across cross section. It does not change over time. UIT, it varies across individual as well as over a period of time. But both are unobserved effect which has impact on the crime rate. Okay, we need to understand the difference between these two. AI and UIT both are like error term, both are unobserved effects that have impact on crime rate, while UIT changes over a period of time. That's why I have T subscript as well. I have not given any T subscript here to represent the fact that AI is basically individual specific time constant. It is not changing over a period of time. Okay. Now, the question is, if we try to apply, so our model is YIT equals to beta 0 plus delta 0 d 2t plus beta 1 xit plus vit equals to AI plus UIT. Okay. Now, for OLS to be applicable, what we need actually, this covariance between xit and vi should actually be, instead of vi, let us say that this is simply v. Should be actually 0. Okay, covariance between x and the error term should be 0, and that is the standard assumption, because if it is related to AI, then that will lead to again endogeneity problem when your explanatory variable is correlated with the error term. So, if this condition has to be satisfied, then what we actually need, covariance between AI and xit should actually 0. So, that means the unobserved effect, this is AI, the unobserved city specific effect should be uncorrelated with the xit. So, that assumption, if it is fulfilled, then only we can apply OLS here. But this assumption is very difficult to be fulfilled, because in reality we actually want covariance between AI and xit to be related actually. Okay, covariance between AI and xit to be related. So, unobserved city specific effect to be correlated with the unemployment rate. So, that is what we want, and basically that is one reason, because of this correlation, since we want this unobserved effect to be correlated with some of the explanatory variable, we actually apply panel data. So, that is what we need to understand. This is same example what we are discussing in our previous chapters when we are talking about instrumental variable estimates and simultaneous equation model. We say that log of wage it equals to beta 0 plus beta 1 education IT plus some AI plus UIT, and we said that in this case AI is basically ability. That is what we said, that individual they have some kind of unobserved ability which also has some impact on their wage rate. And we also what we wanted, that education and ability they are actually correlated. So we wanted covariance between education IT and this AI to be not to have some kind of correlation. If that is what we want, then we need to have this panel data instead of using a cross sectional data. So cross sectional data cannot accommodate the fact that this type of fact that there are unobserved effect. What is the problem? Because the moment we include this and AI is correlated with this model will be suffering from endogeneity bias. We have already discussed. So at the one hand, we need to accommodate the fact that there is the presence of AI in our model, and at the other hand, we also want that the correlation between AI and this to be eliminated, right? So that means we need to transform the model to eliminate AI from the model. How to do that? So how to eliminate, how to remove AI? Because unless we remove AI from the model will suffer from endogeneity bias. We cannot apply OLS. So what we do? We write the equation for both the periods. So for period 2, this would become yi2 equals to beta 0 plus delta 0, because d2t will take the value 1 for the second period, and I am writing for the equation for the second period, plus beta 1 xi2 plus ai plus ui2. And for the first period, yi1 equals to beta 0 plus, this would become 0 because d2t equals to 0 for the first period, beta 1 xi1 plus ai plus ui1. So let's say this is equation 1, this is equation 2. Okay. Now if I take 1 minus 2, so that means if I take the first difference, if I take the first difference of these two, then what will happen? We will get yi2 minus yi1 equals to beta 0 will get cancelled, delta 0 plus beta 1 xi2 minus xi1. This ai and ai will get cancelled, will get ui2 minus ui1. Now if we assume that this y2 minus y1 is basically delta yi, okay, delta yi, this xi2 minus xi1, this becomes delta xi, and this becomes delta ui, then our equation will become delta yi equals to delta 0 plus beta 1 delta xi plus delta ui. Okay, this will be the equation, right? And if we want to apply OLS here, then what we need to do? We need to, for OLS, we need the condition covariance between delta xi and delta ui should be 0. Okay, and this condition is called strict endogeneity. Strict endogeneity. Why it is called strict endogeneity? Because that means we are ensuring not only xi and ui are uncorrelated, but the difference of that also is uncorrelated. Okay, delta xi and delta ui should be uncorrelated. Now, when I say that covariance between xi, delta xi and delta ui, they are not correlated. So, that means this is ensured when xit should not when xit does not have variable like yit minus 1. Suppose one of our explanatory variable is lag dependent variable yit minus 1. If that is the case, we cannot ensure that delta xi and delta ui is uncorrelated. Xi is actually a representation of, this is not xi, a representation of, let us assume that this is a set of explanatory variable. In that set of explanatory variable, if one of the explanatory variable is the lag dependent variable, then we cannot ensure this, because in that case what will happen? This would become yit minus 1 minus yit minus 2, and this would become ui 1 minus uit minus uit minus 1. So, since there is a component called yit minus 1, that would be correlated with uit minus 1. Okay, so we cannot ensure strict endogeneity, this is called strict exogeneity. This is not sorry, this is strict exogeneity. Strict exogeneity. Okay. So, in presence of lag dependent variable, we cannot ensure that this delta xi is actually correlated with delta yi. Okay. Right. Now, second thing, when you are estimating this type of equation delta yi, so our equation is delta yi equals to delta 0. What is our equation? Our equation is delta 0 plus beta 1 delta xi, delta 0 plus beta 1 delta xi plus delta ui. Now, second condition for OLS to be applicable, what we require, that there should be enough variation in delta xi. Okay. So, that means basically what it says, that delta xi should change over a period of time. If it does not change, then what will happen? If it does not change, if any of our explanatory variable is not changing over a period of time. For example, let us say that in our model we have some qualitative variable like gender. So, gender also does not change over a period of time. So, when we take first difference, the variable which are not changing over a period of time, that will also get eliminated along with AI. Otherwise, all time constant variables get removed with AI while taking first difference. Okay, so while taking first difference, we must ensure that in our model there is no variable which is time constant. First difference model cannot accommodate the fact that some of our variables are actually not changing over a period of time. Secondly, even if the variables are changing, they should change at a different rate, because if the variables should change, variables should not only change but also change at a different rate. If the variables are changing at the same rate, they will also get eliminated along with AI. Okay, they will also get eliminated, because when I am taking the first difference between second period and first period, they will also get eliminated, right? So, change should not be the same for all cross sectional units. Okay, variables should not only change but also change at a different rate for all the cross sectional units. Right. So, we must ensure while applying first difference transformation of this type of model that all the variables are changing, for all the cross sectional units. If some of the variables are not changing for some of the cross sectional units while taking first difference, those units would be dropped. Okay. So, number of observation will go down. For example, if it is unemployment rate, and let us assume that for Chennai and Delhi the unemployment rate are not changing, then Chennai and Delhi would be dropped while taking first difference. Similarly, if the variables are changing at the same rate for all the cities, that is also undesirable in this first differencing of the panel data model, right. So, if these conditions are satisfied, that means xi does not contain any variable which is lag dependent one like yit minus 1. If that is the case, we cannot ensure that this is uncorrelated with the error term even after first difference. And that condition, while the condition, that means when we are saying that covariance between delta xi and delta ui, they are not correlated, that is called strict exogeneity. So, that means we are not only ensuring exogeneity at level, but also at their first difference. When covariance between xi and ui is 0, covariance between xi and ui is 0, that is called exogeneity condition. And when covariance between delta xi and delta yi is 0, that is called strict exogeneity. Why it is called strict? Because this is the stricter version of the exogeneity condition. We are not only ensuring exogeneity at level, but also at their first difference. And this is satisfied when there is no lagged dependent variable like yi t minus 1 in the model. So, this is the first condition, and in the second condition we say that delta xi should change. So, all the variables should change over a period of time. Okay. So, if that is the case, then only, so there should be enough variation in xi. Okay, sorry, here instead of delta xi, this is actually xi, because then only delta xi would become some non-zero value. Okay. All right. So, if these conditions are satisfied, then only we will say that OLS is applicable to estimate this type of model. Of course, there are several limitations of this first difference model that we will discuss in our next session. Thank you.